if we look at the example here, we've actually got the parent nucleus transmuting into the daughter nucleus, but we're releasing here gamma rays which are of less power. So that's the most powerful gamma ray, least fast alpha particle, least powerful gamma ray, fastest alpha particle, and the absolute fastest would be just a final drop straight to the daughter nucleus. And that is it right there. No gamma ray or kinetic energy to the alpha particle. So that's that plus energy bit, gamma rays. That's the symbol you can use for gamma. It's the Greek letter gamma. Look like, I don't know, looks like Y. It's hard to draw, but I'll get what you mean if you do that in the exam. Okay, beta decay. Beta decay, there are two types. There's beta positive and beta negative. We'll start with beta negative, which is an electron. Now when there's too many neutrons in an atom, i.e. you've got too much strong nuclear force, a neutron in an unstable atom will split, and it splits into a proton, an electron, and a neutrino. Now the proton remains in the nucleus, hence why when you look at radon going to AC actinium, hold on, just let me check the periodic table. Radon, ACAC, yes, actinium, good, I got that right. So radon going to actinium, you'll note that the mass number stays the same, 228 to 228, and that's because neutrons and protons weigh the same. But the proton number, the atomic number, goes from 88 to 89, and that's because you've gained a proton in here because one of the blues has become one of the reds, and an electron shoots out along with also a neutrino. Now, there's no actual measurable change in mass. I mean, yeah, I suppose there is, you know. If you look on the formula sheet though, there is a slight change in mass. This is a stage 1 nuclear radiation lecture that I've dropped into stage 2. But the electron is 1,840 times lighter, so there is a slight change in mass. And then you've got this. This is this neutrino snake in with a basket on. So when you've got an electron beta minus here, then you're going to have a neutrino, and you have to put the line above the little snake looky thing. Electrons can also be represented with 0, -1, and then an E. And that is because E is for electron, -1 is the charge, because that would normally be a +1 for a proton, and then the 0 represents the fact that it has no mass, even though it does. It's 9.11 by 10 to the negative 31, or 911, or however it is you remember it, Andrew. So that is how beta minus decay occurs. So that's a stream of negative electrons coming out. Now, right, okay. This is the antineutrino, by the way, with the line on the top. So negative for electron, negative for antineutrino. So you got a neutron, a proton, an electron. So neutron becomes proton, electron, and antineutrino. And the other thing too is that the charge is conserved, because you've got a here that would represent the neutron, but it's becoming here a proton, which would be +1, plus an electron, which is -1, and the antineutrino, which is 0. Also, the nucleon number is conserved. Nucleons refer to the number of protons and neutrons. So here we've got 14 carbons. 14 carbons. You've got a mass number of 14 there. Carbon was 6 protons, and 14 for the nitrogen. Got 7 protons there, but the mass number is still maintained. And for the purposes of this equation, your antineutrino and your electron have no mass. The electron and the antineutrino fire out at really high speeds, but the nucleus is almost stationary, and then it will move ever so slightly. But I mean, it's like when you jump and land on the planet Earth. The Earth moves with you, but it only moves slightly because you're so much smaller than it. So the electron and the antineutrino, they achieve such high speeds because it's a lot of energy and small amount of mass, even though we regard them as being massless here. And the nucleus is almost stationary because it's like a giant planetary body compared to the size of those things. And again, with beta emission, the daughter nucleus can actually exist at a higher energy state at one of its discrete energy levels, so that can result in a gamma emission too. Obviously that would then result in like the electron coming out with less kinetic energy, and that the difference would then be represented in a gamma ray. Now, let's try and write an equation to represent the beta minus decay for polonium-218, and then determine the unknowns here and here and all around there.